put together this program for you. We're looking forward to a lot of interesting talks and discussions during the day. The program is roughly laid out into three parts. In the first part, we're looking at advances and challenges in VQA. We're starting off with Professor Lana Lazebnik, who's going to be telling us a bit about specialized knowledge for vision and language tasks. Marcus Rohrbach from FAIR, who's going to be talking about end-to-end module networks. Professor Kate Sanka, who's going to be telling us about explaining and diversifying captioning models. Professor Derek Hoem, who's going to be telling, and in particular, both Derek and Anton's talk are about challenges and dangers in VQA, about what we may be missing and what we may want to think about next. The second part of the day of the program is about the 2017 VQA challenge. So we have a quick 10-minute presentation about the Eval AI platform that we used this year. We built it out of the Cloud CV project. It was out of my lab that we used to host the challenge. And then, of course, an overview of what did we find in the challenge, analysis of the results, announcement of the winners, and talks by the winning teams. All the winning teams and the runners-up, we're awarding NVIDIA GPUs, so please stick around for that. After lunch, in particular, we are looking to look towards the future. So where is this headed? I think there's a theme emerging where a lot of speakers are talking about interaction, a back and forth interaction with humans. Sanya is going to be talking about teaching machines to describe images with human feedback. Jason has a background in natural language processing and machine learning. He's going to be talking about unifying QA, dialogue, VQA, and visual dialogue. Abhishek Das is going to be talking about visual dialogue, and Hugo La Rochelle is going to be talking about a guess what game, which is fairly an interesting setup. At the end of the day, we have a panel session with all the invited speakers. I recommend you to stick around for that, ask any questions. We're in particular looking at what's missing, where we're going next, and then we'll just close for the day. One quick logistical note. To the poster presenters, all of the workshops, so posters for all of the workshops are in the same location. They're downstairs where the main conference posters were. Areas will be marked by the conference organizers during the morning break, but please put up your poster at the soonest whenever the area is already marked, hopefully by the morning break or the lunchtime. So. Last year, we had given out these VQA T-shirts to all of the invited speakers, and I see Marcus showing dedication wearing that T-shirt. So all of the poster presenters, invited speakers, please pick up. We'll hand you your T-shirt, but please if we don't pick it up during the poster presentation. Continuing the self-deprecating status, so from 1.0 to 2.0, the T-shirt this year has 2 images, not one, with opposite answers. And so we have these T-shirts for you, so please pick them up. All right, so with that, that's the plan for the day. I'll hand it over to Aishwarya, who's introducing Lana.
Thanks, Dudu. Our next speaker is, the first speaker of our workshop is Lana Lazebnik. Lana is an associate professor in the Department of Computer Science at UIUC. Lana has done some very influential work in visual recognition and scene understanding. Most relevant to this workshop is her work on joint modeling of images and text. Lana's work on learning joint embeddings of images and text and more recent work on grounded language understanding have been of great importance to vision and language community. Today, Lana is going to talk to us about transfer of specialized knowledge for vision language tasks. We are looking forward to hear from you, Lana.
Thank you. So this is 20 minutes plus 5 minutes questions. Okay, so can you give me like a 5-minute warning or something? Okay, so thank you very much for giving me the honor of going first. So I have not worked too much on sort of full-scale open-ended VQA. But hopefully I will talk about what I see as one of the biggest challenges facing current methods. So what do I mean by specialized knowledge exactly? I don't mean anything too esoteric. I just mean in order to be able to answer any kind of free-form question, what kind of knowledge does a VQA system need to have? So let's give some specific examples. I went through the VQA 1.0 images and questions and try to categorize some of the more common types of specialized knowledge. So in particular, systems need to have knowledge of common object categories, scenes, maybe fine-grained categories, materials, and so on. So almost everybody who works on VQA, their first shot is just kind of train or take an ImageNet trained network, do something on top of that. So we can assume that ImageNet trained networks already have some good deal of knowledge about object categories, but we need more. We need textures, we need scenes, and so on, nouns, if you will. Then, of course, we need a lot of verbs. We need to understand actions and activities. We need to understand what people, animals, and so on, objects are capable of doing, what they might be doing next, and so on and so forth. We need, of course, adjectives. We need all sorts of attributes. So in particular, people are among the most interesting entities that we care about. So we need to have a very good catalog of attributes describing appearance of people, clothing of people, accessories, and so on. Then, kind of stretching our imagination a little bit more, we need to be able to describe motivations. Why are people doing what they're doing? Or, causality. Why is something happening? Something happened before, therefore something is happening now. Maybe somebody fell down, that's why they're sitting in the snow. Even farther afield, there are some questions that have to do with recognizing syntax. So that tends to be a pretty specialized task these days. You really need to build a custom system if you want to be able to read text that's embedded within scenes, or recognize logos, recognize street signs, and so on. What else might we need? There is currently probably small but very interesting category of questions that really can't be answered given the image alone, and can't be answered using purely visual knowledge. You need knowledge of something beyond, common sense facts, maybe knowledge that you scrape from Wikipedia, knowledge databases that are in text form, and so on. So this is what I mean by specialized knowledge. Of course, if we just take a generic network, roughly speaking, trained on ImageNet, fine-tuned in some form on the VQA data set, I think we can all agree there's no hope that that network can really capture all of the aspects of real-world knowledge that open-ended VQA entails. So what can we do? I don't really know, but at present, I know that we have a lot of special purpose data sets that have much better coverage for some forms of specialized knowledge that's very useful for VQA. So things like actions and activities, attributes, materials, and so on. So I will talk a little bit about our work. Attempting in some limited way to use these special purpose networks trained on data sets external to VQA, but that are very useful to VQA. So we haven't worked on the VQA data set. We've worked on the Visual MATLABs data set collected by my collaborators, Alex and Tamara Berg. This is kind of like VQA, but with lots of training wheels. These are fill-in-the-blank questions with only 4 options each, so it's multiple choice. They come sometimes with side information, very useful information like bounding boxes, as I'll show in a moment, and they have predefined semantic types. There are 12 types of questions. Each question has very well-defined semantics that you can use to figure out what knowledge do you need to answer this type of question. So here are some details. This is what one type of MATLAB's question looks like. It's a scene question, and the prompt is always the same. The place is, and you have 4 options. You have to pick one. So what can we do? Well, we can train a network using the MIT SCENES dataset. And MIT SCENES dataset has several hundred scene categories. So you can think of that network as outputting a vector of predictions for specific scene classes. And we just have to somehow relate these vectors of predictors according to the fixed vocabulary of that dataset to the free-form vocabulary of answer choices. And there are relatively straightforward tools for doing that, like CCA. So we can just see, just examine the top predictions from the scene network. You know, scene network thinks it's a train station platform, so it should be very easy to match that to train station as the best choice. There are other questions that are more tricky, like past and future questions. So this is a future question. You're supposed to choose what's most likely to happen next. And because of the way that these alternative answers are selected, the different answers have different subjects. So you have to try to match each subject for each candidate answer and figure out, does it fit the image? Does it look like the image has a bride in it, or a man, or a woman? And that helps you to choose the right answer. And of course, we may also want to detect objects, because some of these answers mention objects. So we want to examine the image, figure out, do these mentioned objects fit the image, and so on. There are other questions that include ground truth regions, and these were also given to the people who provided the annotations that the questions are created from. So if you want to ask, what is this person doing, you need to specify which person, because there might be multiple people in the image. So even to a human, it's going to be ambiguous. But of course, you know, this is a very big crutch, if you will, because we don't need to automatically detect people here. We can just make predictions from an action network and also do some sort of matching from the predefined action classes that we were trained on to the free-form answers. And then there might be other questions about object attributes. We can predict colors. We can train a classifier for colors, maybe other adjectives, and so on and so forth. So this is the flavor of what the Visual MATLABS dataset is and what we do with it. So here is some more detail of how our approach works. So what we do is, given an image, we have our specialized networks, each trained on its own data set, each doing a specific kind of things, like classifying scenes, actions, maybe attributes, and so on. We get the predictions of each of the networks, and then for each type of prediction or cue and each candidate answer, we have to figure out the fit. How does the output of this network, how well does it fit each candidate answer? And for this, we use canonical correlation analysis, or CCA. So it's a textbook technique. You know, from statistics literature, I don't know, maybe even back to the 1930s, but it's really surprising how well it works. We've been able, up till very recently, to beat state-of-the-art approaches with CCA. Now we finally were able to train neural networks to compare images and text, or any kind of paired data from different modalities. You know, you can replace these CCAs with basically trained cross-modal matching networks. We haven't done it. So we get a score from each cue for each candidate answer. We have some scheme for learning weights. We take a weighted combination of these scores, score each candidate answer, pick the best match. So you could, we don't train this end-to-end. You know, we train it in sort of modular way, but you can imagine replacing all of this stuff with neural network modules that can be trained end-to-end, provided there's sufficient data, which MATLAB's dataset is only about 10K images, so it's unclear. So this is what our system looks like. And let me tell you in more detail about some of the cues. Because I think some of these cues and some of the data sets that we use can be also very useful for VQA, general purpose VQA, if you figure out how to work them in the right way. OK, so as far as person-centric questions, meaning questions for which you're given ground truth bounding boxes, there are two types that are important having to do with actions and person-object interactions. So of course, the queue that's the most helpful for that would be a network to recognize actions or person-object interactions. Fortunately, we have excellent data sets for this. There's this HICO data set. HICO stands for Humans Interacting with Common Objects. That was collected at Michigan by Jia Deng's group. It has 600 classes. And actually, the objects in this data set are MS COCO objects, but the data set itself does not overlap with MS COCO. So it could be particularly useful for the VQA data set because the vocabulary is exactly matched. And there's also the MPII data set that has just person actions, about 400 of them. So we have a pretty big vocabulary among these two data sets. There are some differences between them, but they're not super important. OK, so what do we do if we want to recognize, let's say, person-object interactions? So if we look at the person bounding box and just ignore everything else, you know, the person bounding box doesn't always contain sufficient information. In some cases, the object is close to the person or the pose is very characteristic. And if you just look within the person bounding box, you can figure out exactly what's going on. In other cases, like flying a kite, the object could be pretty much anywhere else in the image and the pose is not so characteristic. So obviously, you need some sort of context. And the most natural thing to do might be, you might think, let's try just to detect the objects. But to detect objects, even MS COCO objects, which is still a fairly limited vocabulary, is still kind of hard. I haven't checked the latest method, but latest methods for detection, but you know, a lot of these objects are small. You have a lot of false positives. It's very troublesome to detect objects accurately. So what we did, we decided, well, let's just skip the object part. Let's just do a global context. So if we want to detect a person-object interaction or even an action, so it makes the method quite general, let's just combine features from a person region of interest and a whole image region of interest. So with my student Arun Maria a couple of years ago, we built a very simple network that we call a fusion network. It's based on top of fast RCNN. It just concatenates ROI pooling features from the person box and the whole image to predict person-object interactions. There are a couple of sort of tricks or fine points that we have to use. We have to use multiple instance learning because actually the HICO data set does not give you person bounding boxes, and there could be multiple people in the image doing different things. So we need to use ML. And we need to use person bounding boxes detected up front, but person detection works very well, so we can just assume it's solved. And we also have to use a weighted loss for training because for most actions, in fact, all of them, there's way more negative examples than positive examples. But if you do your training the right way, it's a pretty good network. So here are some qualitative examples of what it does. For each box, it gives separate predictions of what it thinks the person is doing. So in the top left image, the person in the green box, the top predictions are hold knife and wield knife. The person in the blue box doesn't get any predictions because no individual action classifier gets more than 0.5 confidence. So qualitatively, it's good behavior. In terms of quantitative evaluation baselines, we confirmed that our tricks, MIL and weighted loss, help to get better performance. So it's a pretty good network, and as I said, it's very simple. So it gives us the predictions that we need to handle action and person-object relationship or interaction questions. And for those, we, as I mentioned, just ignore the object and it works out fine. Interesting person-centric questions. There are questions about person attributes. Unfortunately, there was, when we were looking at this, no ready-made person attribute data set with a large vocabulary. We did a literature search as of maybe a year or two ago. All existing person attribute data sets had maybe a dozen or so attributes. So here, what we did is we ended up actually using a data set that we ourselves collected that can be very person attributes and maybe other things as well. It's the Flickr 30K entities data set. So it just provides grounding for all noun phrases in sentences in an image. So you get bounding boxes associated with noun phrases. So we scraped that data set for all noun phrases having to do with people and found the people phrases that are the most frequent and sort of cleaned up the vocabulary manually and ended up with about 300 person attributes. So from an image like this, the training data that you obtain would be for, for example, old man, bearded man, man in a blue shirt, and so on. So for all attributes that are frequent enough in our data, we get training data and we can train attribute classifiers. And by the way, for the attribute classifiers, we don't use global image context because attributes are very specific to a person and they get confused if you include global context. So we can predict attributes like skier, little girl, man in white shirt, man in white hat, and so on. So if you're looking for large vocabularies of person attributes, as far as I know, our data set is the largest one out there and can be very useful. Okay, so apart from that, there are some open-ended questions that don't give you ground truth regions. The most intriguing of those are image past and image future. So for that, as I mentioned, candidate answers refer to different subjects, and we don't know where the subjects are in the image. So we have to sort of attempt grounding. For each candidate subject in a candidate answer, we have to find the best fitting person box, and we built a CCA model for that. So on top, if the candidate answer is the man enjoyed his meal, we find the man box as the best fitting box. If it's she was doing some work, then we find the woman's and use that as spatial support to extract features. So you could think of it as a type of attention, but it's not an end-to-end trained attention. It's sort of very task-specific, but it works well. Okay, so when we combine the predictions of all these Q-specific networks together, so we have a scene network we talked about. We also have a color predict combination, we get improvements on all questions considerable having to do with attributes, for example. Really the interesting lessons from this. What's good, what can be the takeaway point? It necessarily needs to go out and work on the Mad Libs data set. The open-ended VQA data set for sure is more interesting. But what's useful? Well, what's useful is that there are very good data sets these days with large vocabularies of knowledge of classes that are useful for general VQA. It's a good idea to train networks on those data sets and somehow incorporate them. What's nice about high-level Qs, we can look at the predictions. What are the predictions for person attributes, for person actions, for scene type, and so on. And human interpretable, so we can understand why our system picked a given answer and not some other answer. Of course, what's bad is that Mad Libs dataset, as I said, it's got a lot take these training wheels off. It's got tell you which knowledge to combine. One of the most challenging things is to sort of understand what is it asking me, where do I need to look, which knowledge do I need to bring in. I don't know yet how to do that. It's also good to have end-to-end methods. So that how to have a single end-to-end. You don't want to have just a pile of separate networks sort of cobbled together in a clumsy way. You need to have one giant network somehow trained on multiple data sets and multiple tasks hooked up to a high-level task like VQA. So recent work, I've seen things on arXiv with and one model to rule them all. I don't know if you guys have seen those. I think it's becoming a topic of interest, how to train gigantic, scary networks on multiple data sets to do multiple tasks in parallel on the same image. I think this is where recognition in general should be going. If you look at an image, you want to understand everything simultaneously, maybe predict scene classes, do some kind of depth map estimation, surface normal estimation if you want. Maybe if you find people, predict actions, predict materials, attributes, and so on. But the work I've seen in this direction just really scares me. And, so I myself don't sort of feel up to tackling this challenge to the fullest, but I think this is where we need to go. And in the meantime, hopefully, the knowledge that I shared and, some of the pieces that I talked to you about can be useful.
We have time for some questions.
Yes?
So I have a question about the attributes that you have collected, sort of scraped automatically. So is that available? And is it like
the attributes?
Yeah.
Available on my student's website. My student, no, I don't think is here.
And that is like
so go to my webpage. There's a link to his webpage. There's a little link to the models. So we haven't done emphasizing it, but yes, it's available.
So that is like also manually verified, or is that?
Yeah, yeah. So basically, he just found the most, grouped the most commonly used person phrases and, manually and so on. So it's manually curated.
And how many was that again?
About 300.
Okay, thank you.
But you can also feel free to take the raw Flickr 30. Do kind of your own mining.
Okay.
What threshold? I think we use threshold of 50 training examples or 30 training examples. If you're willing to lower your threshold, you can get more. You can do something else with it. Okay. And of course, it goes beyond people. So I encourage you to take a look.
Thank you.
Any more questions?
Thank you for the nice talk. And I think I completely can't expect to learn everything from the VQA training set and for 2 years. But I know you said the ugly sense for, even if we ignore all the ugliness of one giant network, or even if we have separate attributes and activities and scenes and objects and surface normals, and we have data sets for all of that, we have networks for all of that. So if you just take the predictions, concatenate that, add a few fully connected layers on top and try and predict answers, do you have a sense for how well that might or might not work?
I think it might work if somebody is willing to do the dirty work. I think it would have like an IBM Watson type flavor. So basically, it would be kind of a very ugly engineering effort. If somebody did it, it probably would work, but this is not what I would like to see happen. And I certainly don't want to touch it myself. So I think in the short term, we just have to do our best. And just kind of see where it goes. But I think we all agree that, it's not realistic, even if the VQA data set was an order of magnitude larger, it's not realistic to expect that it would have full coverage for everything you could want.
Can I just quickly follow up on that? So again, completely agree. You mentioned that, we can cobble it together. And so there's a perspective following on NLP research which suggests that every time you add these intermediate structures and representations and use them to solve some downstream task, it actually just hurts performance, that you're better off just not trying to add these intermediate stages. Do you think that's true for VQA, that it's not, that while using data sets is good as intermediate losses, but forcing intermediate structures may actually hurt downstream performance?
It's very possible, but basically I have no idea at this point how much training data we would need to do everything end-to-end without hand engineering a lot of knowledge. You can probably force it like they forced machine translation, but you know, at this point, I kind of don't have, you know, a very strong sense of the difficulty of this task and how much data it would take. So, but I'm not very dogmatic either way.